It didn't curve the way it should have. The numbers blinked red. The path bent and kept bending. Here's why that matters. An interstellar object falling past the sun should be a slave to gravity, its arc predictable down to the decimal. But 3I Atlas didn't stay inside the lines. It nudged sideways, subtly at first, then unmistakably. The fit failed. The model balked. Something not accounted for was pushing. Astronomers know a few culprits. Comets vent gas when warmed, tiny jets that act like thrusters. Light itself can shove on a surface if it's light enough. Those are textbook answers. But the early data didn't look textbook. No classic comet tail, no easy dust signature, no comfortable explanation. The computed trajectory required a non-gravitational acceleration that refused to sit quietly in the margins. Within hours, a global scramble began. NASA analysts reprocessed station data. ESA's flight dynamics teams ran fresh propagations and got the same unsettling deviation. Ground observatories spun across the planet to lock on. The Very Large Telescope pulled spectra. Radio dishes listened. JWST booked a tentative window, just in case. The message back from the numbers was consistent. The arc was off. Then the story split in two. A group working with high-sensitivity instruments reported a whisper of emissions faint, structured, and wrong for garden-variety outgassing. Others, just as rigorous, called foul. Calibration error, they said. Thermal noise. The signature vanished when they changed their pipeline. Data conflicts piled up on public dashboards. One column flagged unusual glow. The adjacent column labeled artifact. That friction wasn't a side note, it was the headlines. Because if 3I Atlas was venting, the direction of the jets should steer the trajectory in a clear way. If it was being pushed by sunlight, you'd need a very large, very light surface, something thin, broad, improbable. Think about that. The universe has its surprises, but this one asked us to pick between two uncomfortable rooms. ALMA searched for gas species and came back with limits that were too low to account for the shove. VLT saw a muted spectrum with none of the usual comet fingerprints. Solar Orbiter reported the local solar wind behaving normal. So where was the force coming from? Each answer cut down a possibility, and with every cut, the mystery sharpened. In quieter halls, plans changed. The Deep Space Observation Probe, DSOP, was retasked. Its infrared sensors could map heat, trace faint vents, and catch what optical telescopes missed. Controllers worked the math to thread its field of view across 3I Atlas's track. If the shove was real, DSOP could feel it in thermal gradients and tiny flashes of warmth. But even as the probe slewed, the object added a new wrinkle. Photometry showed small periodic brightness ticks too clean to be noise, too irregular to be rotation alone. Some teams saw the pattern, others didn't. The argument widened. Was the signal in the sky or in the software? This is where the doubt became the driver. The non-gravitational push remained. The tail refused to appear. Agencies compared pipelines, swapped raw frames, traded calibration files like lifelines. Admitting a mistake would be painful. Missing a discovery would be worse. So the community made a hard choice. Trust the sky and test the instruments. They would let DSOP take the next shot, peel back the thermal veil, and look inside the enigma that refused to fly by the book. And when DSOP opened its infrared eye, the story deepened. The thermal image didn't glow as expected. It went dark in the center, hollows. Inside an interstellar visitor. Here's why that matters. Natural space rocks, asteroids, comets, whatever they're made of tend to be either solid enough to hold together or loose clusters crushed by gravity and spin into something roughly cohesive. Cavities can form, sure, but they don't survive ejection from a planetary system, the cold soak of interstellar space, and a hard swing past a star. Not intact, not neat. DSOP's infrared maps said otherwise. Bands of cooler temperature traced the silhouette, then dipped away. like the heat had nowhere to hold. 2, maybe 3 hollow zones scattered through the interior, interrupting the conduction of warmth from the sunlit surface. NASA's thermal team double-checked the deconvolution. ESA's image group ran their own pipeline and got the same voids, then argued they were software ghosts from the point spread function. The debate reignited in minutes. Data or mirage? To test it, the DSOP team split the spectrum. Shorter infrared showed one pattern, longer wavelengths showed another. The cavities persisted across both, moving in step with the object's slow rotation. If it was a processing artifact, it would stay fixed on the camera. It didn't. The hollows tracked 3I Atlas itself. Think about that. Empty space inside an object that's been out there for who knows how long. If it were a comet, pockets could form where ice sublimated away, but then the surface should vent and collapse. If it were rock, voids that size should have collapsed under even a whisper of spin. And 3I Atlas wasn't shedding dust, wasn't growing a classic tail. So what was holding those spaces open? JAXA stepped in with cool-headed precision. Their materials group, veterans of small body encounters, offered models of layered ices and organics that could trap heat, crack, and leave pockets. Possible, they said. Unusual, but possible. Meanwhile, ground teams brought in more eyes. ESO's Very Large Telescope pushed visible and near-infrared spectroscopy to fetch a first chemical sketch. JWST's NIR instruments took a cautious peek between other commitments, hunting the telltale fingerprints of familiar minerals and ices. And then the spectrum picked a fight with the models. Key absorption bands didn't line up with common silicates. The features you'd expect from ordinary water ice were muted, shifted, or absent, while a broad, low-contrast slope hinted at complex carbon chemistry that didn't match known comet catalogs. Either this thing has been processed in a way we don't understand, one ESA scientist said off-camera, or we're finally collecting light from a material we've never properly seen before. That's when the whispers started. The cavities arranged along arcs. The temperature differences fell into almost regular spacing. A pattern. Some called it coincidence, produced by fracture mechanics and uneven illumination. Others used a word no one wanted on a mission report. Engineered. The suggestion lit up message threads and shut down meetings. Extraordinary claims. Meet the world's most unforgiving review process. Data credibility became the battleground. NASA's team released raw frames and flats. ESA's group posted their calibration stars and background models. JAXA reprocessed everything independently and got the same broad picture. Hollows where there shouldn't be hollows, and a spectrum that refused to settle into the neat folders of rock, ice, or dust. Critics flagged banding, detector persistence, even cosmic ray hits masquerading as structure. DSOP's operators rotated the spacecraft, changed roll angles, altered integration times. The hollows didn't budge. Here's the unsettling part. If the interior is mostly void, the object's mass is lower than brightness implies. Lower mass should make it easier for sunlight to push it off course, exactly what everyone saw on day 1. A hollow traveler naturally exaggerates non-gravitational acceleration. Elegant. But then the chemistry refuses to cooperate. It's the kind of neat answer that falls apart the moment you touch the next dataset. Agencies staked out positions, all provisional, all public. NASA conceded the cavities were high-confidence features, with caveats. ESA demanded more cross-instrument verification. JAXA urged patience and proposed a thermal fatigue model that could mimic regular spacing without invoking intent. And still, the spectrum sat there, smiling like a puzzle. The next step was obvious and risky. If the hollows were real, they should affect the simplest of elements first. Track hydrogen. Measure what's there and what's missing. DSOP adjusted its plan, tuned its sensors, and turned toward the one signature that could not be faked. The count dropped to 0. Not noise, not a glitch. Hydrogen, gone where it should have been loud. Here's why that matters. Hydrogen is the simplest beacon in space, the easiest to spot, the last to hide. When the Deep Space Observation Probe tuned its instruments to the Lyman alpha signature, the plan was to map a neat halo of escaping gas. Instead, DSOP drew a hole around 3 I-Atlas, a depletion zone, a pocket of less than empty in a sea of hydrogen. That broke the script. Comets vent, asteroids don't. Interstellar debris follows the math. But this was a negative imprint, as if the object were filtering the flow rather than producing it. NASA called it counterintuitive. ESA wanted a calibration check against solar background models. JAXA cautioned that transient solar conditions can fake scarcity, but the hole held steady across multiple passes. It moved with the object. Then the spectrum got weird. DSOP's high-res optics returned sharp lines that didn't land on any periodic table companions features offset from cataloged minerals, ices, and organics. Not the fingerprints of water, CO, or silicates we know. New lines. Or old lines we'd never learned to read. Think about that. Billions of years drifting between stars should sandblast an object down to the familiar. Yet 3 I-Atlas answered with signatures that refused to belong. Ground stations swung into action. The VLT pulled late-night runs to chase reflectance changes. ALMA searched for faint radio tags of simple molecules. Even with its sun angle constraints, teams petitioned to model what JWST would see if it could look. Meanwhile, Solar Orbiter reported magnetic jitters as it crossed the object's projected wake, a small but persistent twist in the solar wind's direction, like a stream curling around an invisible fin. And this is where everything shifted again. Several analysts, quietly at first, then louder on internal calls, argued that 3 I-Atlas wasn't just sitting in the wind, it was shaping it. The depletion zone lined up with a subtle deflection in charged particle flow. The object, whatever it was, seemed to edit its environment. The pushback was immediate. ESA flagged background subtraction issues. NASA's team split on whether DSOP's detector had developed a temperature drift. JAXA reran thermal models that could, in theory, produce spectral oddities through stress-fractured layers and microcavity resonances. The data conflicts sharpened into a credibility crisis. Same object, same moment, different truths. Complicating it all were delays that nobody could finesse. Deep Space Network queues screwed up timing for cross-instrument checks. Packets arrived out of order. A solar storm choked bandwidth just as DSOP's most sensitive datasets needed downlink. Hours turned to days. Interpretations ossified while the numbers trickled in, yet the pattern refused to dissolve. DSOP kept seeing the hydrogen void. Solar Orbiter kept catching magnetic flickers, modest but consistent. ALMA's silence, no simple molecules made the spectral strangeness loom larger, not smaller. It was a negative chorus, signals missing where they should sing and lines singing where they shouldn't exist. Imagine watching a weather vane on the sun's breath, and the vane decides to turn the breeze. That's how the solar wind seemed to behave around 3 I-Atlas. It didn't break physics, but it pressed on its edges. By now the calls had changed tone. Words like anomalous transport, non-classical scattering, and field-coupled architecture crept in terms that sound like lifelines when old explanations start to sink. The need for collaboration was obvious. So were the bruises. Every agency wanted the headline. No one wanted to be wrong. Still, one fact stood, unblinking. Hydrogen was missing where it should be found, and spectral lines were present where none should exist. 2 simple measurements, pointing in the same impossible direction. The next dataset would go beneath the skin. The next dataset didn't bounce. It stacked, layer upon layer, like pages laid with intent. Here's why that matters. Natural bodies accrete messily crumbled ice, dust, fractures, all jumbled by tides and thermal stress. But DSOP's subsurface scans came back with repeating strata, evenly spaced shells, sharply bounded, echoing the object's rotation like a blueprint wrapped around a worldlet. The signal was tidy. Too tidy. NASA ran the numbers twice, then 3 times. ESA asked for raw packets, no filtering, no compression. JAXA's materials team tried to match the pattern to sintered regolith, invoking exotic ices with phase transitions. It didn't fit. The returns showed uniform thickness across huge arcs, then a clean handoff to the next layer, the kind of precision nature rarely maintains on kilometer scales. Think about that. Precision in a place we assumed was debris. Context? Picture an onion. Now make every layer follow a math you can write down on a napkin. DSOP's thermal mapper saw temperature bands that tracked those layers, as if each shell had a different way of carrying heat. JWST, tuned to the mid-infrared, found hotspot lines that pulsed with the object's spin but refused to smear the way a normal surface would. VLT polarization data saw glints, not a smooth sheen, but a periodic reflection that turned on and off like a coded blink. That's when the word engineered crept from late-night email into public briefings. Not as a conclusion, but as a question scientists hated even to ask. Could geology do this? Could evolution of ices and dust do this? Some at CNSA pointed to layered ice in Kuiper Belt fossils, then balked at the uniformity here. ALMA weighed in with quiet data. Chemical signatures were missing where they should have been, present where they shouldn't. Hydrogen scarcity in one shell, a spectral line no one could place in the next. And then, the object pushed back. High-energy particle bursts, short and loud. Solar Orbiter saw the spike's first brief storms that didn't track the sun, but tracked 3I Atlas itself. DSOP felt them as snow. Sudden salt and pepper in the detectors, rising dead pixels, timing counters skipping like a scratched record. Instruments began to degrade. Electronics that had eaten cosmic rays for years suddenly developed nervous tics whenever the scan crossed a seam between layers. Now the conflict wasn't just between agencies, it was within the data. Was the apparent order a trick born of damaged sensors? Or was the damage caused by the very structure they were trying to map? ESA urged caution. Stop active probing before you cook the payload. NASA argued for one more pass at lower power. JAXA proposed rotating the scan geometry to test whether the architecture was an aliasing artifact. Everyone wanted the truth. No one wanted to blink. Theories spiraled. If the layering was real, maybe it was a stress dissipation lattice, a way to survive eons in interstellar space. If it was more than that, maybe those shells were tuned to particles, guiding them, damping them, using them. One audacious preprint suggested isotope balances in the spectra implied formation conditions older than our local stars, a claim so bold it drew both ridicule and quiet fascination. Here's the uncomfortable part. Nothing in the files let anyone fully rule it out. Meanwhile, DSOP's team watched their symbolic ship become the hero and the target. Its subsurface radar meant to peel back ancient geologies was finding a pattern it was never designed to explain. On the ground, scientists argued over calibration constants. In orbit, the probe bled capacity with every burst. The object, silent and indifferent, kept rotating, switching those glints on and off as if counting. And this is where everything shifted again. During one skim, the particle bursts didn't just spike. They sequenced 3 quick, 1 long, 2 quick right as the scan crossed a junction where one layer handed to the next. Was it a message, or merely our pattern-hungry minds at work on a storm of charged debris? The room split. The debate turned raw. They needed a closer look, all at once, from every angle, before the instruments failed or the moment passed. So the agencies set aside the bruises and planned a coordinated close pass run, committing to fly into whatever 3I Atlas was building around itself next. The close pass begins. Cameras lock. The object vanishes. Not gone hidden. A skin of plasma blossoms around 3I Atlas like frost igniting on glass, and every high-fidelity map the teams prepared dissolves into noise. This matters because the whole plan hinged on geometry. Get close, map the surface, resolve those layered seams hinted by DSOP. Instead, the surface goes opaque. The data, again, refuses to behave. Instruments pivot. DSOP drops to plasma modes, trading pictures for particles. NASA routes its magnetometers to fast sampling. ESA's solar orbiter turns to watch the field lines wrap. JAXA's dust analyzer opens a larger mouth. CNSA's spectrometers scan for a window in the haze. From far out, JWST stares through the near-infrared and sees the spectrum flatten as if every feature is being smeared. VLT and ALMA try polarimetry, hoping the glow itself betrays structure. Everyone leans in. And this is where everything shifted again. The shell doesn't just glow, it spins. A stable vortex forms around the nucleus like a tornado without air, a funnel of ionized gas coiling into the darkness. The swirl is steady, almost mechanical, and the field around it surges in steps, not waves. Solar orbiter reports magnetic ramps clean, discrete jumps sweeping past at regular intervals. DSOP's magnetometers hit their ceiling and auto range twice in 1 minute. Here's why that stings. A vortex that's stable shouldn't exist around a body this small unless the flow is being guided, either by shape or by something acting like shape. Remember those engineered layers? The shell blooms exactly at the junction. DSOP flagged earlier the place where one stratum handed to the next. Think about that. The data conflicts come roaring back. NASA's radar-LiDAR hybrid estimates the size of the nucleus has shrunk by 1/3, scattering off the plasma fooled the models, they say. ESA counters with occultation timing. Star dips imply a larger silhouette, not smaller. JWST's team insists the color temperature is rising, suggesting energy injection from within. ALMA shows a narrow line of polarized emission that flips every time the magnetic ramps hit. JAXA reports 0 dust grains over the aperture during the peak of activity, no familiar comet spray, while CNSA claims transient heavy ion traces that shouldn't ride this kind of flow at all. Same moment, different truths. Behind the scenes, the rivalry thaws just enough to triage. Data pools go live. Engineers share calibration files the way climbers share rope. They build a picture from absence, where the shell is darkest, where it thins, where particles slip through. The result is unnerving. The vortex isn't just spinning, it's precessing with a slow, deliberate wobble, like a gyroscope responding to a signal. If the nucleus is turning underneath, it's now masked by a plasma dance so precise the rotation direction itself becomes arguable. Prograde? Retrograde? The numbers fight. The public report takes a jolt to the headlines. A temporary plasma shell, a stable vortex, magnetic surges marching in lockstep. NASA calls it atypical, but natural. ESA leaves the door open to non-standard internal structure. JAXA urges restraint. Social feeds howl. And in the control rooms, the question becomes practical. How do you see through a storm that seems to know you're looking? DSOP tries a trick. Instead of chasing images, it watches the flicker. Light curves don't care about the shell if the shell itself is the story. The probe stares at the glow, and the teams stitch its heartbeat from microsecond blips to minute-long pulses. And there it is. Not random. Brightness rises with each magnetic ramp, falls in sync with the vortex's wobble, then just once stutters in a way the particle detectors echo a moment later. 3 quick, 1 long, 2 quick. Again. Now consider this. A plasma veil that lifts and drops on cue. A vortex steady enough to count. Field steps like stairs. If 3I Atlas can't be seen, maybe it can be read. What comes next isn't a map of the surface, but of the patterns in its light. It repeats. Then it drifts. Not noise, not weather, a pattern. Here's why that matters. Interstellar debris should flare and fade with heat and spin. messy and forgetful. 3I Atlas doesn't. Its light curves fall into steps, then into beats, then into a rhythm that seems to answer the sun's magnetic pulse. That's a contradiction to everything we expect from a frozen rock passing through our neighborhood. DSOP holds the stare. Microsecond blips are stacked into minutes, then into hours. NASA's team flags the phase lock. Brightness rises on each magnetic ramp from solar orbiter, sinks as the vortex around the nucleus tilts, then just once stutters. 3 quick, 1 long, 2 quick, again. The ESA photometry group calls it a structured modulation, careful not to say more. JAXA's analysts point to quasi-periodic oscillations, a behavior seen in plasmas, not in fractured ice. CNSA compares night-side data and finds the beat survives even when the plasma shell thins. Think about that. A light that remembers when its veil lifts. JWST turns in, searching for chemistry. The spectrum is wrong in all the familiar ways, but there's a new wrinkle. The color swings line up with the stutter, nudging from redder to bluer in step with the brightness gates. VLT adds polarization measurements. The light isn't just brightening, it's twisting its orientation, shifting like a wind vane in a storm. ALMA listens for molecules and hears something stranger. No clear lines, but a faint continuum wiggle that slips in time with the optical beat. Different eyes. Same drum. And this is where everything shifts again. The pattern isn't constant. As 3I Atlas races outbound, the beat stretches, a slow motion chirp. If it's a signal, it's changing its clock. If it's natural, the clock is the environment. Solar Orbiter reports the magnetic steps relaxing with distance. Right behind it, the modulation relaxes too. NASA and ESA lean toward mechanism, a plasma skin acting like a shutter, magnetically pumped and gating sunlight in quantized bursts, a natural transistor in space. But the message crowd doesn't fold. 312 repeats just often enough to be tempting, and the engineered layering from earlier maps sits in the back of everyone's mind like a loaded question. Data conflicts don't vanish. They pivot. Some instruments log the stutter prominently, others barely catch a murmur. Calibration wars flare and cool. JAXA's team shows that when they rephase the signals to solar orbiters' field vectors, the disagreement shrinks. Now consider this. If the field is the baton, then 3I Atlas isn't speaking, it's playing along, a resonator shaped by those curious layered interiors DSOP saw. A structure that amplifies certain frequencies and chokes others. A device, perhaps. Or a geology we've never modeled. ESA's theorists sketch an overlooked pathway. In deep interstellar space, layered volatile pore shells can charge separate and build a stable plasma envelope. Near a star, that envelope couples to the magnetic field, turning the whole object into a magneto-optical modulator. No engine required. No intent implied. A cosmological mechanism hiding in plain sight because we've never watched the right kind of traveler up close. But the doubt remains, and maybe it should. The hydrogen depletion zone still refuses easy explanation. The spectral lines still don't match our books. The engineered look of those layers still hangs in the air. ALMA's wiggle, JWST's color step, VLT's twisting light, each dataset is a door with 2 labels, physics and purpose. The agencies do something rare. They agree to leave both labels on. Then, almost politely, 3I Atlas fades. The plasma veil thins and doesn't return. The vortex unspools. The beats stretch until they blur into ordinary starlight. DSOP watches until the numbers become background, and the background becomes silence. It leaves the solar system unchanged, but not us. In its wake, new math for light curves, a fresh playbook for plasma, a blueprint for listening when you can't see. Was it speaking? Was it only singing the sun's song through an alien instrument? The documentary answer is honest and small. We don't know yet, but now we know how to ask.